This is section 8.4, Translating Power Functions, and we are on page 344 in your textbook. So we need to do a little bit of a review before we get started. We did this briefly a couple chapters ago. First things first, we're just graphing an absolute value graph. That looks something like this. Remember, it's just a V. The second line we're going to graph is up 2 spaces. We should be able to remember that because remember these equations are in slope-intercept form, and we're just saying that our y-intercept is going to be positive 2. And likewise, now we have a y-intercept of negative 2, so we've slid our original graph down 2 spaces. When we graph this, remember our original was just like a graph and it was a V. Now with a positive 2 on the inside of that, whoops, sorry, wrong direction, we move 2 to the left. And with a negative 2, we move 2 to the right. So if you want to take a second, back up if you need to, I would go ahead and copy examples of each of those graphs, maybe just like a y equals x, and just do a quick version of each of those in your notes, just to remind yourself that's supposed to be up to. It's kind of hard to tell. Anyways, just do those real quick so you have those to refer back to. So translation. So translation of the graph of a function is a sliding of the graph without any rotation or resizing. That means if we start out with this, it's not going to flip upside down. And if we start out with this, it's not going to become either narrower or wider. We're just talking about the slope, or I'm sorry, the graph moving up and down or left and right, which looks like I have like snowflakes going all over the place or something, but just remember, it's none of these things. It's not flipping. It's not getting narrower or wider. The translation is just moving up, down, left, or right. So a power function is a function of the form y equals a times x to the nth power, where the base x is a variable, while the exponent n and the coefficient a are constants. So example 1. And I promise you, just like every other lesson, that definition will make more sense once we're done here. So it says graph the function y equals x squared. So first we need to make a table of the ordered pairs. So we'll have our x, and we'll have our x squared. Remember, our x squared is also our y value, because we said y is equal to x squared. So if we have negative 3 as a value, negative 3 squared would be 9. If we have negative 2 as our x value, negative 2 squared is 4. Negative 1 squared is 1. 0, well 0 squared is just 0. And then we start moving back up. So we've got our negative 3, our negative 2, our negative 1, 0. So now we'll do 1, 2, and 3. So 1 squared is 1, 2 squared is 4, and 3 squared is 9. So when we go ahead and graph this, we'll plot the points. And when we are talking a function that is squared, or our power function that we were talking about, it's combined with a smooth curve. So plot the points and connect them with a smooth curve. So this isn't like our absolute value that was a sharp V. This one is a smooth curve. This curve is also called a parabola. So in this graph, our vertex is at 0, 0. Example 2 says graph the function y equals x squared, y equals x squared plus 2, and y equals x squared minus 3. Well, we've already done y equals x squared. That was the last graph that we just did. So there it is for you. Now, if you take a look at the chart on page 345, what they've done, they've taken the same graph, or the same chart or table that we just did with the -3, -2, 1, -1, 0, 1, 2, and 3 and our x squared values. And then they've done another row for the x squared plus 2 graph and another row for the x squared minus 3 graph. So we would do x squared for -3 would be 9, plus 2 would be 11. The -2 squared would be 4, plus 2 would be 6. -1 squared would be 1, plus 2 would be 3. 0 squared is 0, plus 2 would be 2. And you can follow along for the rest of the graph. Then they did the same thing with x squared minus 3. And then we plot each one. So we have x squared plus 2. We plot our points, and we'll see that it actually moves just our whole parabola up 2 points. So our new vertex is at 0, 2. And when we have x squared minus 3, we plot that graph, you'll see that it's actually the same thing, except this time it's moved down 3 spaces. So, more about translations. A translation of a function results when a number is added to or subtracted from either the input or the output of the function. In general, given y equals x squared plus k, the graph will shift k units vertically. That's what we just saw. The example 2 showed us that our plus k will move our graph either up k units or down k units. So for example 3, we have y equals x squared. Then we have the quantity of x minus 2 squared and the quantity of x plus 3 squared. They're doing the same exact type of deal again with a table for our ordered pairs. This time they went a little bit farther. They started at -4, did -3, -2, -1, 0, 1, 2, 3, and 4. They are taking the quantity of x minus 2 or x plus 3 and then squaring that. And you will see that for the quantity of x minus 2 squared, that's going to move our graph 2 units to the right. And for the quantity of x plus 3 squared, that's going to move our graph 3 to the left. So in this case, when we have x minus h all squared, the graph will shift h units horizontally. So this following chart applies to various types of functions. And the chart is on the bottom of page 346. So we talk about different types of translations. There are vertical and horizontal. So remember we said the plus and minus k gives us our up or down or a vertical shift. So plus k, adding k after performing the base function, will go k units up. Negative k after performing the base function will move us k units down. Positive h before performing the base function moves us h units to the left. And minus h before performing the base function moves us h units to the right. This is super, super, super important. You guys have seen the big formula sheet that I carry around from when I was in school that has like 2 pages of front and back, crazy colored functions and formulas and everything else. This is definitely one of those things that I have on there. So make sure you have this written in a safe place. You will use this again and again and again. So this says given y equals the quantity x minus h squared plus k, the graph will shift h units horizontally and k units vertically. So you can have these two things combined in one function. The vertex, or the turning point of the function, will be located at hk. So y equals x minus 2 squared plus 4. Horizontal translation of 2 units to the right. And the vertical translation will be 4 units up. That means our vertex will be at 2, 4. So you can tell this just by looking at it. Likewise, we have y equals x plus 3 squared minus 2. The translation of this will be 3 units to the left and 2 units down. So our vertex will be at -3, -2. And again, just so a refresher, we're looking at these numbers. This number is telling us what way we're moving sideways. A positive value tells us to move to the left, which I just spelled left completely wrong, good grief, left. And this one is telling us whether we're moving up or down. This one's telling us to move down 2 units. The up and down makes a whole lot of sense if you just think about it, it's positive or negative. The left and right is actually opposite of what you think it would be. So positive values move to the left, negative values move to the right. So the graph of y equals x to the third can also be drawn using a table of ordered pairs. The point of inflection of this graph is at 0, 0. You will see that in just a second. So we are on page 347, kind of in the middle of the page. And we have, in general, the point of inflection of the graph of y equals the quantity x minus h cubed plus k is located at hk, similar to the power function that we looked at just before this. So if you look, we have a chart there in the middle of the page that's x values and x cubed values. You have to remember, if we are cubing a negative value, that's a negative times a negative times a negative, which is going to result in a negative value. That's why we see the second side go down rather than scooping up like we saw before. So example 4. On the bottom of page 347, follow along with me to study the graphs of the following functions and complete the table describing the translations in reference to the base function y equals x to the third. So we're working with a base of y equals x to the third, which they actually did for us above here with the chart that they used the -2, -1, 0, 1, and 2 values. Then they give us y equals the quantity of x minus 4 cubed plus 5. And we see that this will be translated 4 units to the right. So remember, our negative value here means to go right. And 5 units up, because our positive value here tells us to go up. So we're going to the right 4, up 5. So the point of inflection, or this point in our graph, is going to be at 4, 5. That would be the red line they put on the graph. Then we have, compared to the same base graph, we have y equals the quantity of x plus 5 cubed minus 2. So this positive value tells us we are going to go to the left 5 units. This negative value tells us to go down 2. So the inflection, or this point on our graph, is going to be at -5, -2. And here are those graphs for you. So this is our points of inflection. We have 0, 0. This was 4, 5. And this was -5, 2. Okay, so that's actually it for this lesson. Go ahead and take a look at the examples. Again, if you need to, let me know if you have any questions, and then get started on your assignment.